This conversation is powered by Google Illuminate. Check out illuminate.google.com for more. Welcome to our discussion on the fascinating world of physics education and open educational resources, OER. Today we'll be delving into two technical papers that showcase the use of Tracker, a free video analysis software to study kinematics, specifically the constant velocity of an air puck. What immediately strikes you about the use of OER in physics education?
The beauty of OER, like the Tracker software highlighted in these papers, is its accessibility. It levels the playing field, providing students with powerful tools regardless of their financial background. This allows for a more inclusive and equitable learning experience, something incredibly valuable in physics education.
The first paper shows a simple HTTP response, indicating a successful retrieval of data. What kind of data might this be, and why is the content encoding zip header significant?
That HTTP response suggests the server successfully sent a web page. The content encoding a zip tells us the data was compressed using zip to reduce the size of the transfer, making it faster to download. This is a common optimization for web servers.
Second paper is more interesting. It shows a web page snippet, seemingly from an OER platform, featuring a lesson on constant velocity using an air puck and tracker. What are the key advantages of using an air puck in this type of experiment?
Air pucks minimize friction, allowing students to observe motion closer to the ideal case of constant velocity. This simplifies the analysis and helps students grasp the fundamental concepts without getting bogged down in complex calculations involving friction.
The webpage mentions Tracker software. Can you explain for our listeners what Tracker does and how it helps in analyzing the air puck's motion?
Tracker allows users to import video footage and track the movement of an object, in this case, the air puck. By identifying a point on the puck in each frame, Tracker generates data points representing the puck's position over time. This data can then be used to calculate velocity and acceleration.
The papers mention constant velocity. How is this concept represented graphically, and what does it mean in the context of the air puck experiment?
Constant velocity means the object's speed and direction remain unchanged. On a position time graph, this is represented by a straight line with a constant, non-zero slope. In the air puck experiment, a straight line would indicate that the puck is moving at a constant speed in a straight line.
What are some potential sources of error that students might encounter when using Tracker to analyze the air puck's motion?
Several factors can introduce errors. Inaccurate calibration of the video scale is a major one. Blurring of the puck in the video can lead to imprecise position readings. Even variations in air pressure affecting the air cushion and less friction can impact the results.
How does the presence of friction affect the idealized model of constant velocity? How would this be reflected in the data obtained from Tracker?
In reality, friction will always be present, causing the air puck to decelerate slightly. This would be reflected in a slightly curved position time graph where the slope, representing velocity, gradually decreases over time. The idealized model assumes zero friction, resulting in a perfectly straight line.
Second paper includes a study guide with short answer questions and essay questions. What is the pedagogical value of such a study guide?
The study guide provides a structured approach to learning, reinforcing key concepts through different question types. Short answer questions test comprehension, while essay questions encourage deeper analysis and critical thinking.
One essay question asks about the importance of minimizing friction. Why is this crucial in the air puck experiment, and what practical steps can be taken to reduce its impact?
Minimizing friction is crucial because it allows students to focus on the fundamental principles of constant velocity without the complexities of frictional forces. Steps to reduce friction include using a smooth, level surface, ensuring sufficient air pressure for the air puck, and potentially even conducting the experiment in a low air resistance environment.
Another essay question compares the motion of an air puck to an object in free fall. What are the key differences and similarities between these two scenarios?
The key difference lies in the forces involved. An air puck on a level surface experiences negligible friction and balanced vertical forces, gravity and normal force, resulting in horizontal motion. An object in free fall experiences only gravity, resulting in vertical acceleration. Both can be analyzed using Tracker, but the resulting graphs will be very different.
How can Tracker be used to verify Newton's first law of motion, inertia? Can you suggest a simple experiment?
Newton's first law states that an object in motion stays in motion unless acted upon by an unbalanced force. Students could use Tracker to film an air puck gliding across a nearly frictionless surface. The nearly straight line on a position time graph would demonstrate the puck's tendency to maintain its velocity, illustrating inertia.
What are the limitations of using video analysis software like Tracker, and how do these limitations affect the accuracy of the results?
Limitations include the accuracy of the video itself, resolution, frame rate, the precision of tracking the object, and the calibration process. Errors in any of these steps can propagate through the calculations, affecting the accuracy of velocity and acceleration measurements. Careful calibration and multiple trials are essential to mitigate these errors. The study guide's inclusion of error analysis is crucial for developing scientific rigor.